Alright, hello boys and girls, welcome back. The last time I had done an example of a simple question in probability, and I told you how you can design a probability space, the events, and the probability measure, how you will go about designing that for a simple example. Now I'll take up a bit more of a complicated question and I'll solve that by constructing a probability space and using the axioms of probability that we had defined before. Alright, let's get into the question. So given a dice, 6 sides, it has been thrown thrice. So you have a dice, same dice has been thrown thrice. Find the probability of a sum 7. Okay, so that means given 3 throws and the numbers recorded in those 3 throws, you have to find the probability that they add up to 7. Okay, understood? Now the first thing, as usual, while solving it using the axiomatic approach, is that we'll be constructing a probability space. So the probability space is any triplet that is omega fp, with omega being the sample space or the set of all the possible outcomes of this experiment. And what are the possible outcomes of this experiment? Well, it's a 6-sided dice, it has been thrown thrice, so we need something that will give us information on all 3 throws or all the 3 numbers. And the most simplest thing you can think of is a list, that is d1, d2, d3, which denote the numbers of the 3 throws, and that's exactly what I've used as an elementary event or a single outcome of the trial. And so the sample space is basically all possible triplets of this form d0, d1, d2, such that each component is a number between 1 and 6, and because of that, the size of the sample space, that is how many elements are there, is 6 cubed, that is 216. Why? Because each component has 6 possibilities, and so because of that, you just multiply 6 3 times, and that gives you 6 cubed, that is 216. And as usual, the event space, that is f, the collection of all possible events, is basically 2 raised to omega, that is all the possible subsets of the sample space. So it's pretty clear, because using these elementary events, you can pretty much construct all the subsets, all the possible subsets of the sample space. And so the event space, that is the collection of all the possible events, is basically the set of all subsets of omega. Now, how to assign the probabilities? So we want to assign concrete numbers, and that's what this example is about. I'll be designing a probability measure, and it's not as complicated as it sounds. So as I explained before, this probability measure, that is p in the omega fp triplet, that is something that is up to us to design. It just needs to follow particular axioms, the axioms that we've defined before. It just needs to behave as per how we have told it should behave, and however we design it is totally up to us. And for the sake of the example, I'm choosing something simple. So the probability measure associated with each elementary event, that is d0, d1, d2, is 1 over 216. So essentially what I mean to say is that each of the outcomes are equally likely. Simple enough? Okay. So for the outcomes which provide us sum 7, we want the triplets such that d0 plus d1 plus d2, they add up to 7. And the possible values that d0, d1 and d2 can take is between 1 and 6, 1 and 6 also included. And there is a brute force way of doing this on paper, or there is a much more clever way of doing this. I'll explain the brute force way of doing this. So what all numbers add up to 7? And so let's do this. Let's see, 1 plus 1 plus 5, now that's 7. So if d0, if 115 is a triplet, then obviously 151 and 511, they'll also be valid triplets. And so for 115, you have 3 possible extra combos that come as a free bonus. And so we can keep in our mind the number 3. We have already found 3 triplets which satisfy this d0 plus d1 plus d2 equals 7. Next, what about 1, 2, 4? Well, 1 plus 2 plus 4 is also 7. And now this 1, 2, 4 can be rearranged in 6 different ways. So if 6 different permutations are possible, they're also valid triplets, right? Since the numbers are same, just that they're rearranged in a different way. And so 1, 2, 4 has 6 different ways of arranging it, 6 ways. And so we can add to the number I told you to keep in your mind, that is 3. You add 6 to that, that's 9. We have found 9 triplets which satisfy this condition. Okay, let's bring out another one. What about 2 plus 2 plus 3? That's also 7. So in this case, this 2, 2, 3 can be rearranged in 3 different ways, just like 115. It can be rearranged in three different ways to provide 3 new valid combinations that give you a 7. So that is 9 plus 3. We have found 12 combinations, 12 triplets that add up to 7. Now there is another one. That's 3 plus 3 plus 1. That's also 7. And that 331, similar to 225, can also be rearranged in 3 different ways to give you 3 new triplets. And that way, 12 plus 3, that's 15. We have found 15 different triplets that give you this sum of 7. And now I did it by hand. I mean, if instead of 7, I had asked you to find the triplets that satisfy this for a bigger number. Instead of 7, let's say I asked you how many of these triplets add up to 15. Now that would be very difficult, right? 7 was pretty short. There were only 15 combos that would give you 7. But for 15, there might be a lot more combos. It's not going to be easy. And so there's actually a much more clever way to do this. So for each d0, which can take a value between 1, 2, 3, 4, 5, 6, it can take one of those values. What about this? You create a polynomial, that is x plus x square x raised to 6. So each of these terms represents that this x raised to 1 represents that it can take a value of 1, and x raised to 2 values basically represents the fact that this d0 can take a value of 2, similarly all the way to 6. So this x square, x plus x square, x raised to 6, this is a polynomial for d0. So similarly, you multiply with it the polynomial for d1 and d2, which will be similar because d1 and d2, they also take values that are 1, 2, 3, 4, 5, 6. And so you multiply all of them. Now, understand why I've done this. Consider the terms that multiply and add up to give you a multiply and add up for x raised to 3. So how many terms are there? So how many x raised to 3 forming terms are there? There's only one of them actually. So x multiplied with this and this. So there's only one x cubed term, and the coefficient of x cubed is basically 1. Now what does that represent? That represents the fact that there's only one way to create x cubed, and that's reflected by the fact that there's only one triplet that adds up to 3 in this case. That's 1, 1, 1. There's only one triplet. So similarly, if I ask you to find the coefficient of x raised to 4 in this whole polynomial, you'll observe that the coefficient is actually a representative of the fact that it will give you the number of ways in which you can add 3 numbers which add up to 7. And so just like that, to find the coefficient of x raised to 7 is tantamount to finding the number of ways you can add 3 numbers to sum up to 7. And this technique, this polynomial over here, it's actually called a generating function. And in that case, what we can do is find out the coefficient of x raised to 7 in this whole polynomial. So what is that polynomial? The polynomial is actually x cube, I took a common out of all of them, x cube times 1 plus x square all the way to x raised to 5. Now, since there is an x cube term outside, instead of finding x raised to 7 coefficient in the whole thing, I can just find an x raised to 4 coefficient by removing the x cube in this thing. In this reduced polynomial, I can find the coefficient of x raised to 4. Now, this can be written as this. So 1 plus x raised to n is basically 1 minus x raised to n over 1 minus x. That's a geometric series thing. So the sum of a geometric series can be written like that, and so it can be written as a product of a binomial polynomial and another negative binomial actually. So a negative binomial because there is a minus 3 exponent, and so if we use the binomial expansion to expand this term, we'll get this, a summation from n equal to 0 to 3 of all of this inside, and this over here will actually be an infinite term polynomial. This over here can be expanded by the negative binomial expansion like so, and if we move in the summations outside over here and move the terms together, this over here is the summation. And so if we want to find the coefficients of x raised to 7, we just need to find out what all terms give us 6n plus r, x raised to 4. We want to find out the coefficients of x raised to 4. So we just need to find out which all terms in the double summation give you 6n plus r equals 4. And mind you, n can take a value between 0 and 3, and r can take a value from 0 to infinity. Now, which combination of n and r give you a sum of 4, this 6n plus r equals 4? Well, it turns out in our case we are lucky to have only one combination of n and r which give us 6n plus r equals 4, and that is n equal to 0 and r equal to 4. The coefficient, that is this whole thing, corresponding to x raised to 4. So if 6n plus r equals 4, then that basically gives us a coefficient or a term containing x raised to 4, and the coefficient of that term is given here, minus 1 raised to 4, 3c0, 2 plus 4c4, and that comes out to be 15. So we got the same answer that I did by writing on pen and paper using the generating functions. So there are 15 possible triplets that give us a sum of 7, and hence, since each triplet has a probability of 1 over 216, and each triplet is also an elementary event, and all these elementary events are mutually exclusive, by the third axiom, you get the probability of sum 7 as 15 over 216. So look at how I have applied this axiomatic approach, which was purely theoretical, did not deal with concrete numbers, but with a few assumptions that I made, which was that all the outcomes are equally likely, all the possible outcomes of the trials are equally likely. I've got you the probability of having a sum of 7 in this case. So if I had chosen a whole different assumption to construct my probability measure, then I might have gotten a whole different type of number over here, and maybe the sequence of calculations that I might have needed to do might have also been different. But in this case, I chose the probabilities this way because it's very simple, and I got to illustrate a pretty nice technique to find the number of ways to add 3 numbers to give you a particular sum. So for people who don't want to do all this complicated stuff, you can obviously do it by hand, not a problem at all. I'm not saying it's a bad way, it's actually a pretty good way as well. But for people who want to show others that they know their stuff in mathematics, you can go and do it with the generating function. I've already illustrated the steps on how to do that. And with that, let's end this video. In the next video, I'll be showing you how the axiomatic approach is compatible with your frequentist approach. With that, thank you.